Hello everyone. You can tell I am exhausted. Yeah, I have been recording lecture videos and classwork videos to help students along whilst we are supposed to stay off the roads. I hope you're staying warm, and I'm going to keep this very short. Just a reminder, please start reading chapter 2 so that you can follow the things we are doing or we will be doing in class next week. There is a new classwork that's out, so please take a look at it and try your hands at it if you have some time. Now on Monday I will continue the lecture and do a little bit of classwork with you. Yeah, so we have a full plate. Let's jump in. Like I said, this will be very, very short. Okay, chapter 2, the overview of chapter 2. What you can expect to see in chapter 2 is the simple regression model. We are going to jump into, well, some things we have already seen in chapter 1, and then make our way to properties of the ordinary least square. We will look at goodness of fit as it concerns the simple regression model. And then we will take a pause so that I go over what we are doing before I jump into the second part of chapter 2. Okay. What is the simple regression model? A simple regression model has only one explanatory variable. A simple regression model has only one explanatory variable. All right. Well, we have here y equals beta 0 plus beta 1 times x plus u. What is y? Y has multiple names: dependent variable, explained variable, response variable, predicted variable, regressand. Interesting. Well, x also has multiple names: independent variable, explanatory variable, control variable, predictor variable, regressor. Okay, so we check y, check x. Beta 0 and beta 1, what are those? Now in blue, beta 0 and beta 1. Beta 0 is the intercept, beta 1 is the slope. We don't know what these are, so we are trying to estimate them. We are trying to estimate beta 0, the intercept, and beta 1, the slope. What does this mean? Think about it this way. We believe that the random variables x and y have a relationship, some relationship. We don't know what kind of relationship. So we want to find the intercept, where that relationship possibly starts, and the slope, the rate of change of that relationship. You see what's happening here? Yeah. And then we have the u. The u is the error term, the disturbance, and contains unobservables. In u, we may have observable variables and unobservable variables. Okay, observable variables because maybe we made a mistake and left out a relevant variable, and so that relevant variable is in u, or it's just a variable that we don't observe, and so it will be an unobservable variable in u. Okay. Pause the video, go back and listen to what I said if it's getting a bit hard for you, but I hope you are reading that textbook. All right, what's this? Well, this is coming from the previous slide. Y equals beta 0 plus beta 1 x plus u. Like I told you before, we are interested in knowing two things about the relationship between the random variables x and y. We want to know where that relationship starts, beta 0. And we want to know the rate of change, the slope of that relationship. Slope is calculated as change in y over change in x. That you know. You understand that very well. But what about this u? And how did they get this to look like that? Those of you who have done some calculus, this is what is happening. Now, if you haven't done any calculus, I have an explanation for you to just hang on. So for those of you who've done calculus, what they're doing is finding the partial derivative dy dx, and well, beta 0 is a constant, so that goes to 0, and then you have b1 beta 1x, so that's beta 1, right, plus du dx, and what we hope is that is 0, so that we can identify our slope to be beta 1. Now, given that, so those of you who haven't done any calculus, right? Given that we have the error term here, and we know that we may have some observable variables and unobservable variables in u, our interpretation that beta 1 is the slope will be correct if all other things are held constant when we are trying to find that slope. Cast your minds back to the previous lesson when I was designing an experiment with you in the class, trying to find the impact of various measurement of fertilizer on growth of a plant. You remember what we did to get all else to remain constant? Yeah, we tried to fix that. We tried to create an equal playing field for each and every plot, or each and every potted soil, if you can remember that example. So someone reminded me to add the control, right? So here we have the control. How about I start with that control? And then we have experiment 1, 2, 3, and maybe I think there was a 4th one. We said in each of these planters we will have the same quality soil, we will have the same amount of water, the same exposure to sunlight. Do you remember that? Yeah. Now if you go just one slide down, you can see in U, rainfall, quality of land, presence of parasites in the soil. Do you see that? Yeah. If we can get these to remain constant, then our beta 1 will truly be the slope measuring the impact of fertilizer on yield. Do you see? Okay. So like I said, these are some things we have already seen. If we are unable to have all else remain constant, it will be very, very difficult to just look at beta 1 and say truly that is the slope. It will be a noisy measure of the slope. It will not be even close to helping us get the slope. It will be way off. The slope may be 2 and it will be like 30. See, it will be way off. Now, in the second example, where we have wage equals beta 0 plus beta 1 times education plus U, we are trying to find the impact of increasing education on wage. If you increase your education, how should wage respond on average? That's what we're trying to find. Now, in U, what is there? Well, labor force experience, work ethic, intelligence. Like I told you last class, you really cannot observe intelligence per se in the data that's in front of you in Excel. Like how do you know observation 1 is more intelligent than observation 2? You don't know. So well, that's on the next slide. Let's go on to the next slide. So how do we get an interpretation that we can label causal? That, hey, increasing education causes your wage to go up. In this particular example, we cannot say increasing your education will cause your wage to go up. All we can say is more education is correlated with higher wages. That's what we can say. So why can't we say it causes? More education causes increase in wage. We can't say that because in U we have intelligence. Now, in this particular case, education and intelligence are going to be highly correlated, in the sense that more intelligent people or more educated people are more likely to be more intelligent. So that correlation between the X, which is education, right? This is your explanatory variable, and your U, that correlation exists. So the backdoor path will not be closed. The backdoor path will be open. By the way, when I cross through this arrow between U and X, it means backdoor path closed, right? When I leave it open, it means, or uncrossed, it means backdoor path open. So the chances that the backdoor path between X and U will be closed like this, it's highly unlikely, because we did not set an experiment, we did not create the experiment fixing what we need to fix across all the across the control and the treatment units. See that? So it's going to be hard to believe that the backdoor path is closed. What would it mean for the backdoor path to be closed so that we can say there is a causal interpretation? Well, that will mean that there is zero correlation between X and U, meaning the explanatory variable contains no information about the average of the unobserved factors. So education should not contain any information about the average of an unobserved factor like intelligence. But that is highly unlikely. By the way, this is termed the conditional mean independence assumption. We started with this, y equals beta 0 plus beta 1 x plus u. We started with that. We don't know what beta 0 is. We don't know what beta 1 is. We are trying to estimate that. But say I tell you what beta 0 and beta 1 is, because, well, I'm this deity that can see things, I'm this oracle that can see things beyond what the human eye can observe, okay? So with that oracle, say I tell you what beta 0 and beta 1 are. Well, in that case, then you can obtain this population regression function where we have the average value of the dependent variable y being expressed as a linear function of the explanatory variable. And that is happening by way of the zero conditional mean. There is more on this. The population regression function looks like this, where this blue straight line is that average y equal beta 0 plus beta 1 times x. What is this saying, or what does it mean? And how do we interpret the average value of y? So again, say an oracle can tell me what beta 0 and beta 1 are, where I'm trying to estimate them, but I don't know what they are, but an oracle told me the answer. Well, in that case, I can plug them in there and pick one of the x's and then find the average value of y at a particular x. Say the average of y at a particular x, 3.6, is 3.3. What does this mean? Well, here we are looking at high school GPA and its impact on college GPA, right? So what we are not saying here is every student that has 3.6 GPA will have 3.3. We are not saying that. What we are saying is pick a slice out of the data. So, well, at Georgia State University, say you have the class of seniors, right? You take their high school GPA and then you take their college GPA they are graduating with, you put it all in a table, right? Say you pick the seniors that have or that had 3.6 GPA in high school. Will all of them have 3.3 GPA? No, the average will be 3.3 GPA. That's what this means. So therefore, in the data, you will find some seniors who have their college GPA above 3.3 or below 3.3. Take your time, pause the video, read the slide, and see what I'm saying. Why will everyone not have 3.3 GPA? And why would 3.3 GPA just be the average, with some people falling above the average and others falling below the average? That's because of unobserved factors. that someone with a high school GPA of 3.6 went to college and came out with a college GPA that probably fell above or below or at 3.3. All of that depends on unobserved factors in you, the error term. Unobserved factors like what? Unobserved factors like access to tutoring. So in that case, maybe the college GPA will fall above 3.3. Unobserved factors like illness, that could cause the GPA to fall below 3.3, the college GPA to fall below 3.3. You see that? Yeah, that's all we are saying. That there's a distribution of college GPA above and below 3.3 for students who had a high school GPA of 3.6. Okay. I will stop here and I'll have you watch the video and I'll have you read the textbook chapter 2 and take a look at that second classwork I posted on iCollege, and we'll see each other on Monday. Okay? Stay warm and I guess good morning. It's 1:43 a.m.